This video is for class 9 physics, and today we are discussing thermal expansion. Almost all substances, solids, liquids and gases expand on heating and contract on cooling. We have studied this part here again in class 7, right? So the expansion of a substance on heating is called thermal expansion of that substance. There are three kinds of thermal expansions, right? They are linear, superficial and cubical, which we have studied, okay, earlier also. Linear expansion, superficial expansion and cubical expansion. We are not going in detail in these three kinds of expansions because our syllabus is targeting to the anomalous expansion. A solid has a definite shape, so when a solid is heated, it expands in all the directions. That is, it can increase its length, area and volume, or increase on heating. The increase in length is called the linear expansion, the increase in the area is called the superficial expansion, and the increase in the volume is called the cubical expansion. The liquids and gases do not have a definite shape, so they have only one kind of expansion, and that is the cubical expansion. Only the volume expands. On heating, gases expands much more compared to the liquids and the solids, while liquids expand more than the solids. Some substances such as water from 0 to 4 degrees Celsius, silver iodide from 80 degrees Celsius to 141 degrees Celsius, right, and silica below minus 80 degrees Celsius contracts on heating. They do not expand on heating, it contracts on heating, right? So they are not following the rule, they are going against the rule, right? And expand on cooling. Reverse thing is happening here, right? This kind of phenomena is called anomalous expansion, right? Anomalous expansion means abnormal expansion. The expansion of a substance on cooling in a certain range of temperature is called anomalous expansion of that substance. We shall study the anomalous expansion of water. So we shall study the anomalous expansion of water only. So here this substances here, water, silver iodide or silica, does not contract on cooling, right, and does not expand on heating. But that is not true for all the temperatures. They have a certain range of temperature, in that range only it shows that abnormal behavior, but for other ranges it is normal, okay. So let us study the anomalous expansion of water. So if we take some water at 0 degrees Celsius, and start heating, we find that it contracts instead of expanding, right, in the temperature range only from 0 to 4 degrees Celsius, but after 4 degrees Celsius it behaves normally. On heating further above 4 degrees Celsius it expands. So in this range it is contracting, right. Similarly, if water initially at the temperature above 4 degrees Celsius is cooled, it should contract, right. Suppose it is at 12 degrees Celsius, while coming to 4 degrees Celsius it will contract till the temperature of the water reaches 4 degrees Celsius. On further cooling, that is below 4 degrees Celsius to 0 degrees Celsius, it shows abnormal behavior, it expands. This unusual expansion of water on cooling, it is in the temperature range 4 degrees Celsius to 0 degrees Celsius, is called anomalous expansion of water. Thus the expansion of water when it is cooled from 4 degrees Celsius to the 0 degrees Celsius is known as anomalous expansion of water, abnormal expansion of water, right. Now figure 6.1 shows the variation in the volume of 1 gram of water with temperature in the range from 0 to 4 degrees Celsius, 0 to 10 degrees Celsius, the volume of water first decreases on heating it from 0 to 4 degrees Celsius. So while the temperature is rising here from 0 to 4 degrees Celsius, it is contracting, okay, right? So the volume decreases, right? And then on further heating, right, that is above 4 degrees Celsius, the volume increases. Okay, let us go to the graphs. So here we are having two graphs. Let us see the first one. Okay, the first graph is between the volume and the temperature. As you can see, the temperature rises from 0 to 2 degrees Celsius. You can see the volume is decreasing, right, from 1.001 to somewhere around here, right? And as it is reaching 4 degrees Celsius, the volume becomes 1. So here what you can see is the volume is decreasing when it reaches 4 degrees Celsius. But after 4 degrees Celsius, when it reaches 6 or 5, 6, 7, 8, 9, 10, what we can see is we can see the gradual increase in the volume, right? So here you can see this kind of graph. We can see this graph here. The graph shows abnormal expansion, okay, or contraction, right, while it is being heated, right? So here this is a graph, okay, and we can draw the same kind of graph between the density and the temperature also. As you all know, the density is equal to the mass by volume, as mass will remain constant during the change in temperature. It's constant, right? And it's constant, okay, mass is constant. So if the volume is increasing, the density should decrease, right? So let's see what happens to the graph when we draw between density and temperature. So variation of density in water when the temperature changes. So first what happens is the density will increase as the volume is decreasing, isn't it? And then the density starts decreasing because the volume is increasing. Is the opposite of the previous graph, right? This is the graph which shows the variation between density and temperature. So I hope you have understood the graph portion, okay. There's a experiment which proves the anomalous expansion of water, which demonstrates the anomalous expansion of water. The experiment's name is Hope's experiment. Let us go through that experiment, Hope's experiment, to demonstrate that the anomalous expansion of water. This particular experiment also has two kinds of graphs. Please pay attention while teaching that graph, okay. So in 1805, okay, the scientist T.C. Hope devised a simple arrangement known as Hope's apparatus for demonstrating the anomalous expansion of water. Figure 6.3 shows the Hope's apparatus. The apparatus consists of a tall metallic cylinder provided with two side openings, P near the top and Q near the bottom, fitted with the thermometers T1 and T2 respectively. The central part of the cylinder is surrounded by a cylindrical trough containing a freezing mixture of ice and salt, right? Freezing mixture of ice and salt, so the cylinder is filled with pure water at the room temperature, okay. The temperature recorded by both the thermometers is observed at a regular interval of time. Let us go to the figure, okay. Here we can see the apparatus, okay. Here we can see the apparatus. So here we can see the holes, that is P and Q, one at the top, the other at the bottom, fitted with the thermometers T1 and T2. And we have a metallic trough. This is the metallic cylinder, and the metallic trough where we have a freezing mixture. Its temperature is nearly minus 22 degrees Celsius. Okay, the freezing mixture has a temperature nearly minus 22 degrees Celsius. So here the cooling starts from this particular trough, okay. So let's see what happens. Let's see the observations, okay. So here what we have done is we have poured water, okay, in this particular cylinder, and we are trying to cool it and try to absorb the recordings of the thermometer. Let's see what happens. So here are the observations, okay, of the thermometer of the experiment. So initially both the thermometers T1 and T2 show the same temperature, that is the room temperature. So this is the temperature shown by the thermometers, okay, when the experiment has just started, okay, when they have just plugged into the holes, right. So they show the same temperature. Let this temperature be 10 degrees Celsius, okay. Suppose they show same temperature, that is 10 degrees Celsius. So initially what is happening is the temperature shown by the thermometers are 10 degrees Celsius. First, after some time, obviously, first the thermometer temperature recorded by the lower thermometer T2 starts decreasing, and finally it becomes steady at 4 degrees Celsius, while the temperature recorded by the upper thermometer T1 remains almost unchanged during this time, that is, it remains at suppose 10 degrees Celsius. This is our observation. We will try to understand why. Okay, so first thermometer, what happens is the remains same, that is T1 remains same, the temperature shown by T1 remains same, that is 10 degrees Celsius, but the temperature shown by T2 gradually decreases and becomes steady at 4 degrees Celsius. Okay, let's see why. Now, while the temperature recorded by the lower thermometers T2 remains constant at 4 degrees Celsius, okay, then the upper thermometer T1 shows a continuous fall in temperature up to 0 degrees Celsius. It is showing up to 0 degree Celsius, and then it also becomes steady. Okay, thus finally the temperature recorded by upper thermometer is 0 degrees Celsius and the lower thermometer is T2, that is 4 degrees Celsius. Figure 6.4 shows the variation in the temperature recorded by thermometers T1 and T2 with time. So we will come to this particular point afterwards. Let's understand what is happening. Okay, coming to the figure 6.3, that is Hope's apparatus, let us try to understand the observations which you have seen. The first observation was both the thermometers initially are showing a certain temperature, that is room temperature. Okay, let this temperature be 10 degrees Celsius. So initially both the thermometers, that is T1 and T2, are showing 10 degrees Celsius. Observation 2 says that the temperature in the upper thermometer remains constant, that is 10 degrees Celsius, but the temperature recorded by the thermometer T2 will decrease up till 4 degrees Celsius. Let's see why that is happening. Okay, as you all know, a freezing mixture is kept here at the center of the cylinder, whose temperature is nearly minus 22 degrees Celsius. Here, this ice right here with mixed with the salt. Sorry. Now, the cooling of water starts from this region. As the cooling of water starts from that particular region, okay, now as you all know, the whole water is at 10 degrees Celsius initially, so water here will be at 9 degrees Celsius. So what happens is 10 degrees Celsius will decrease to 9 degrees Celsius, right? I hope you have understood here. But as you all know, 9 degrees Celsius water is slightly heavy compared to 10 degrees Celsius, because the density increases as the temperature decreases. So slowly this 9 degrees Celsius water here, somewhere around here, will be heavy, right? Somewhere around here will be heavy, and it will descend down, thus pushing the lighter water up. Okay, here. Now what happens is slowly this cycle will continue, right? All 9 degree will come here, and all water at a higher temperature will go up. Okay, now then what will happen at a certain point, the whole cylinder from this portion, right, from the mixture, below the mixture, the whole water will become 9 degrees Celsius, right? Now slowly it starts cooling more, then slowly it becomes again 8 degrees Celsius. Now this time the water at 8 degrees Celsius is heavy compared to water at 9 degrees Celsius, because the density of water at 8 degrees Celsius is more compared to the density at 9 degrees Celsius. So like before, the water at 8 degrees Celsius will come down and the 9 degrees Celsius will rise up. So this process continues, okay, till it becomes 7 degrees Celsius, then 6 degrees Celsius, 5 degrees Celsius, and then 4 degrees Celsius. So ultimately what happens is, all the water here below will become 4 degrees Celsius recorded by the thermometer, right? But the temperature above the freezing mixture is still 10 degrees Celsius. Why? Because this water is lighter, isn't it? This water is lighter now. So now again the cooling will start. That is our third observation. Okay, what happens in the third observation is, the lower thermometer will show 4 degrees Celsius, but the upper thermometer is showing the fall in temperature till 0 degrees Celsius, and then it becomes steady. Okay, let's see why. Now this freezing mixture still continues to cool the water, which is at 4 degrees Celsius. Now suppose it becomes 3 degrees Celsius. Now from 4 degrees Celsius it is becoming 3 degrees Celsius, right? Now this 3 degrees Celsius should go down. Will it go down? No. Why? Because 4 degrees Celsius water is heavy compared to this 3 degrees Celsius. So this 3 degrees Celsius will remain here, isn't it? Right? So slowly it becomes 2 degrees Celsius, which is much more lighter. Slowly it becomes 1 degree Celsius and starts cooling this particular portions of water also, right? And ultimately the whole water will reach to 0 degrees Celsius and it becomes steady. And if it cools further, if we take the observation further also, then it starts freezing also from here, right? So this was the explanation for the particular observations which you have just gone through. Let us go through its graph also. Now coming to the graph portion, here you can see, right, there are two graphs. This is for the first thermometer, the upper thermometer. This is for the lower thermometer, right, that is T2. Now as you can see from our observation, initially the temperature of the temperature shown by the upper thermometer did not change, right? So it's a flat line, so temperature did not change. But after a certain point, what happens when the lower thermometer showed 4 degrees Celsius, the temperature starts falling down. Okay, it is shown by this graph. And for the thermometer 2, that is the lower thermometer, initially the temperature falls down. Okay, the temperature decreases, but it becomes steady when it reaches 4 degrees Celsius, because at this point the water becomes heavy, right? So I hope you have understood this particular explanation of Hope's experiment, right? Now coming to the consequences of anomalous expansion of water. Like Hope's experiment, here also we can understand the anomalous expansion of water helps in preserving the aquatic life during the very cold weather. In cold weather or winter, when the atmospheric temperature starts falling well below 0 degrees Celsius, water at the surface of the pond or lake, initially at the temperature above 4 degrees Celsius, begins to radiate heat. Why will it radiate heat? Because it is cooling, right? The hot objects lose heat to become cold. So since it is more than 4 degrees Celsius, right, so it starts radiating heat, provided the temperature outside is below 0 degrees Celsius. Now once it starts radiating, it starts becoming cold, so the temperature of water starts falling up to 4 degrees Celsius. When the temperature of water at the surface falls, water contracts, so its density increases, and therefore it sinks to the bottom. This continues till the temperature of the entire water reaches to 4 degrees Celsius. Now further cooling of top layers below 4 degrees Celsius results in the expansion of water, and so its density decreases. As a result, water does not sink further, but it remains on the surface. When the temperature of the atmosphere falls below 0 degrees Celsius, right, then water on the top surface rejects heat to atmosphere and gradually freezes to ice. But the water well below the ice layer remains at 4 degrees Celsius. The water layer just below the ice in contact with it will be at 0 degrees Celsius. Figure 6.5 shows the formation of ice at the surface of the pond or the lake. Since ice is a poor conductor of heat, so ice now prevents the flow of heat from water of the pond or lake to the atmosphere. Thus temperature of the water in contact with the ice is at 0 degrees Celsius, while the temperature of water layers below the ice gradually increases to 4 degrees Celsius. As a result, fish and other aquatic creatures remain alive in water or pond or lake through water, though water on the surface has frozen into ice. Nature thus protects the aquatic life during the winter season also. Okay, let's see the figure. Okay, coming to the figure, suppose the atmosphere around this lake is suppose minus 5 degrees Celsius, right? Atmosphere around this lake is minus 5 degrees Celsius. Now what happens is, because of this minus 5 degrees Celsius, the water which was initially probably at 6 degrees Celsius starts cooling, right, starts losing heat. So before the ice crust is formed, so what happens, slowly it becomes 5 degrees Celsius, the 6 will be dropping to 5 degrees Celsius, and slowly it becomes 4 degrees Celsius. Then all the water will be at 4 degrees Celsius, right, including this ice crust also. At that time the ice crust is not formed, so it will be at 4 degrees Celsius. Now slowly what happens is, still the cooling continues. When the cooling continues, probably this uppermost layer first becomes at 3 degrees Celsius, right. So as you all know, this 3 degrees Celsius, okay, is lighter compared to the 4 degrees Celsius, the water I am talking about. So it will not come down, it cannot displace this 4 degrees Celsius, but slowly it becomes 2 degrees Celsius also. Slowly it becomes 2 degrees Celsius. So when this layer becomes 2 degrees Celsius, the water below, just below it, might be, this layer might be at 3 degrees Celsius, but the lower layers still be at 4 degrees Celsius, because 2 degrees Celsius water also cannot displace the 4 degrees Celsius water. Now it becomes 1 degree Celsius. Now when this becomes 1 degree Celsius, this layer, second layer, might be at 2 degrees Celsius, and this particular layer might be at 3 degrees Celsius, right. Still the cooling continues. So now what happens is, the topmost layer might be at 0 degrees Celsius, then the layer in touch with it can be also at 1 degree Celsius, right. Then another layer will be at 2 degrees Celsius, the another layer will be at 3 degrees Celsius, but still the water here will be at 4 degrees Celsius. Now still the, suppose still it continues to cool down, okay, the temperature falls. Now suppose the upper layer starts freezing, okay, the upper layer starts freezing. Now the water just adjacent to that layer will be at 0 degrees Celsius, this layer will be at 1 degree Celsius, then this layer might be at 2 degrees Celsius, this layer might be at 3 degrees Celsius, but the lowermost layer here, at least this space, will be at 4 degrees Celsius. Now as you all know, this is a bad conductor of heat, the ice is a bad conductor of heat. So now further cooling also, it will not let the heat from the water come out, right. So the heat is trapped inside the water only. Now the aquatic life will be alive, these fishes will be alive at 4 degrees Celsius. So I hope you have understood this formation of ice at the top of the pond, right. Now let us go to its next consequence. The next consequence is that the anomalous expansion of water is responsible for the burst of water pipelines and destruction of crop during the very cold nights, right. So in winter nights, as the atmospheric temperature starts falling below 4 degrees Celsius, water in the pipelines expand. As you all know, when the water cools from 4 degrees Celsius to 0 degrees Celsius, starts expanding. So it expands and it exerts large pressure on the pipes, causing them to burst. Plants also die for the same reason, as the capillaries burst when the water expands below 4 degrees Celsius. Suppose we consider this as the capillary or the mouth of a pipe, and we have water, and we have water here, and we have water here. So what happens is when the temperature falls below 4 degrees Celsius, this starts expanding. When it starts expanding, what happens? It has no space to go, so hence the pipe will crack or it might burst. Same thing happens with the capillary also. So this much for this video. Thank you so much.